We're going to do example 21.4 from the book. Now this is a good problem because it involves Faraday's law and Lenz's law and flux and change in flux. So we've got to do a whole bunch of different things here. Now a couple things to remember. Flux, which gets the symbol phi b, is equal to the magnetic field times, or the area, I guess, that encloses the magnetic field times the magnetic field strength. And if this is not perpendicular, then you've got to include the sine of the angle between it and the normal to the face of the loop. But these are perpendicular to each other, so you don't have to worry about it. Now, question A says determine the rate of change in flux. Well, the rate of change in flux is delta phi over delta t. In our case, that's going to be 0 minus whatever we started with. And it ends at 0 because this whole loop comes out of the magnetic field, and if there's no magnetic field, then there's no flux. So 0 minus 0.05 squared, that's the area, times 0.6, that is the magnetic field strength, over 0.01, nope, just 0.1 seconds, because it takes 0.1 seconds for it to come out of the field. Now, this is going to get us 0.05 squared times 0.6 divided by 0.1, 0.015. 0.015. Now this actually has units of Webers per second, the rate of change of magnetic flux. Magnetic flux is measured in Webers. 1 Weber is equal to 1 Tesla meter squared. So when you take magnetic field times an area, you get a Weber. When you divide that by time, you get Webers per second, and that describes the rate of change of magnetic flux. Oh, and this is negative because 0 minus that. Now, part B says, what is the EMF in the whole loop? Well, according to Faraday's law, the EMF, E, is given by the opposite of the number of coils times the rate of change of the magnetic flux. And I really should put a sub B on there. Over delta t. And so all I have to do is take this negative 0.015 times negative 100, because negative 100 is the negative and 100 is the number of loops, times negative 0.015 gets us 1.5 volts. We took the number of loops, Webers per second. Okay, EMF is a voltage, so 1.5 volts. Now, part C, oh, we're not quite done with part B. Part B got us a voltage. It also wanted us to find the induced current. So we get a potential difference of 1.5 volts. Remember Ohm's law, V equals IR, that will allow us to find the current, because they did tell us that the resistance is 100 ohms. So all I have to do is take my 1.5 volts divided by my 100 ohms of resistance and get 0.015 amps are going to flow through that loop. Now, what direction will they flow? That is an interesting question. Remember, Lenz's law says that the current will flow in a direction that produces a magnetic field that will try to maintain whatever magnetic field is there. So as this thing pulls this way, we're getting less magnetic field into the page. So we're going to want more magnetic field into the page. And in order to do that, the magnetic field that's enclosed, the magnetic field that's going to be generated, has to be into the page, inside the loop. Okay? So if the magnetic field is into the page, then I can use the right hand rule. If I point my thumb in the direction of current and curl my fingers, they curl in the direction of magnetic field. And so the current is going to be induced in such a way that it flows this way and this way, which is of course clockwise. So this 0.015 amps is clockwise in direction. Now, part C says, what's the energy dissipated? This is an interesting thing. Remember, energy is the rate at which work is done. And the energy in a circuit can be found by taking the power. Well, power is energy over time, right? And so if we take power times time, we'll get energy. And the power consumed by a circuit, power equals voltage times current, which we can do. We've got 1.5 times 0.015. So 1.5 times 0.015, 0.0225. This is, of course, watts. That's the power. Now, this was going to happen for 0.1 seconds. So we're going to multiply this by 0.1 to get it to energy, times 0.1 is 0.00225 joules of energy. Now, question D says how much force is actually required to pull this out. There's a couple ways to do that. Remember, work is force times distance, and that is equal to the change in energy. So if we know this much energy was used, that much work was done. So we could say 0.00225 is equal to the force times the distance. Well, the distance we had to go to get it completely out of there is 5 centimeters, so 0.05. So we could take our 0.0225 or 0.00225 divided by 0.05, and we get 0.045. 0.045 newtons of force required. But we could do this another way. Remember, the force that acts on a wire is equal to NILB, number of coils, times the current, times the length of the wire, times the magnetic field. Now, we don't actually have to worry about the force on these two, because the force on this wire, if we point our fingers in the direction of the current, curl them in, the force here is down. And then over here, the force there is up. So the force up and force down cancel each other. And so the only force we have to balance, to overcome or whatever, is that one in order to pull this thing out of the field. And so we're going to take this equal to 100 times the length, but we're only worried about this length perpendicular to the field there. And so that is 0.05 times the current. The current we found up here is 0.015 times the magnetic field of 0.6. And if we do this, 100 times 0.05 times 0.015 times 0.6, we get 0.045 newtons. So it doesn't matter if you use conservation of energy or if you use the force acting on a wire in a magnetic field. You can get the correct answer here either way.